Okay, so let's take a look at what you are supposed to be doing for lab 5. And we have you do have some pre-lab work that you're supposed to do. Now, if you have not installed Vivado, I highly encourage that you do that. It will make your life easier. You can test things at home before you come to lab, minimize your time in lab, really make doing your project easier. It's a bit harder to install it on a Mac than on a PC. I did post the instructions for doing that, but do expect that it will take a while if you are going to try to set that up. So I'm going to walk through some stuff actually using Vivado. If you don't have Vivado, then you need to do your pre-lab work using a text editor. So if you're on a Mac, that would be text edit. If you are on a PC, let's see, what do we have these days? Probably Notepad. Let's just see, Notepad. Yeah, there it is, Notepad. You can just type it in Notepad. If you use a word processor, then you'll end up with like extra stuff in there that you don't actually see, and you just want to have the characters. That's gonna be true anytime that you're trying to copy something into an editor for some sort of programming language. Okay, so the first thing that you are supposed to do is to write the Verilog for a D flip-flop. So I'm going to go through the stuff for this lab, and then I'm going to post some videos separately with some more detail about individual aspects of Verilog that may help you out. But these videos are just specifically for getting you some help for lab 5, which is not a hard lab, by the way. It's pretty easy. So lab 5 is you are looking that we're going to use the code on page, and we're told to use a non-blocking assignment inside the always block. And then we have this note here: in general, it may be more convenient to use a non-blocking assignment for a state transition of a sequential circuit. Do not use a non-blocking assignment for a combinational circuit, as it may cause errors. So a sequential circuit where you're using the flip-flops, then non-blocking is usually going to be good. When you start doing finite state machines, you're going to want to use non-blocking assignments. And notice that what in Verilog, when we are setting a new value of Q, then we say that Q, in this example, Q equals D. You can write the Verilog, you come up with the characteristic equation, and you can put the characteristic equation on the right-hand side. So for a D flip-flop, the characteristic equation is just D. That's really easy. But if you have another kind of flip-flop, like for this lab, you're supposed to design your own kind of flip-flop, you'll have to come up with what the characteristic equation is if you want to set up your Verilog that way. And we'll talk about what that means later. Okay, so we have to write the Verilog, and we also have to set up the constraints files. And the constraint files will tell what switch and what LED we want to use on the actual Basys board. So first we start Vivado, and I always forget it's all the way down in Xilinx. And I installed this last year. I don't know what the current version is. It does seem to take a while to start. Okay, now I always refer to Let's see if I can get to it. It's a very nice guide that your professor made that is in lab resources. So we have using Vivado with the Basys3 board. I always have this handy, and I just kind of follow it step by step every time, even though I think now I have it all down pat, but it's just gonna make sure that you get everything right. So first thing we do is create project. And then it's going to be next. And I give the project a name. And let's see, I think we are supposed to call this, we have name your project lab 5_1_ alpha beta. So lab 5_1_ it's just me. So I'll do RR. So that's what we're supposed to use. That's from the lab directions, which were right up here for the name of the lab. And then next. And then if you look in the guide here, on this step, you want to use an RTL project, and you'll want to check the box, do not specify sources at this time. And then next. And then here, now this information is all on that handout that I just showed you. How to get to the correct information for the hardware that we're using. But under family, it's Arctic 7. Under package, it's CPG 236. Under speed, it's -1. And then the one you want is this middle one with the A35. And again, all of that information is right here. So we've got that right there in that guide. And then next, and then finish. Now, if you don't have Vivado, all of this stuff that we're doing right now, you can't do that. You're going to just wait till we get to the part where we do the text entry for the source code, and then you'll do that. You'll do that in a text editor, and you'll bring that with you. So we now need to add 2 files. We need to add our source file and our constraint file. So I'll add the source file. So let me just go back, show you what I did. Up here under sources, under project manager, I did plus, and I'm going to add or create design sources next. And we are supposed to call it DFF_alpha beta. So create file, DFF D flip flop _ RR. Okay, and finish. And I'm just going to say, okay, at this point, you can actually establish the names of some of your inputs and outputs. I find it easier just to do that later. So just say, okay, and then yes, and then constraints. So now I'm going to add a constraint file. So I clicked, I clicked on constraints, and I clicked on plus, and I'm going to click on add or create constraints. And let's see, use any name ending in alpha or beta for your constraints file. Oh, so I was just reading from this. Use any name ending in alpha beta for your constraints file. So add create constraints, create file. I actually usually call it the same thing, DFF_RR. It'll have a different extension, so it will be a different file. Okay, and finish. So notice that we have under in my sources, under design sources, I have 1. Under constraints, I have 1. So I have my DFF_RR.v, and I have my DFF r_rr.xdc. So when you create your own file using a text editor, you can either just give it those extensions and save it like that, and then import it, or it's probably just as easy just to save it as a text, and then when you get to the lab, do what we just did here, and then just copy and paste it in. Okay, so now I'm going to go to the source, and notice it put some stuff in here, some comments, and it started it for me. It gave me my module name, and it's ready for me to put in my inputs and outputs, and it'll let me know if I have some errors when I'm putting it in. So right now I am supposed to use inputs D, clock, and output Q. So I'm going to put D, Q, and I use _CLK. Keep in mind, whatever you are calling your clock, that's going to be, that variable is what you're going to be using when you set up in your constraints, when you tell the board that you're actually using a manual clock. You have to make sure you know what your variable name is. Is it underscore? I mean, is it lowercase CLK? Is it uppercase CLK? Yeah, what is it? Keep that in mind. Okay, and then I'm closing parentheses and semicolon. And notice when I do that, right away, I start getting some red squiggles, underlines, telling me I've got an error. And the error is because, oh, it had already put this in for me because it thought I was going to put my inputs and outputs down here below, which I didn't do. I put them in up here, so I can take this out. And you say, oh, well, but I still have an error. Now, if I hover over this little red over here, it's telling me my error is that D is not declared, Q is not declared, and clock is not declared. Correct. I haven't declared them yet, so hopefully when I declare them, that'll go away. Okay, so now indenting is very important, not because it's going to change how the compiler works, although Python does. Python, the actual white space matters, but that's the white space doesn't matter for how it works, but it matters a lot in keeping track of what's going on with your program. If you don't indent right, you can't tell if you are in the correct program block, if your begins and ends line up. It is very important to be neat in your programming. So our outermost level is module and end module. Everything else is going to be indented from that. And then anytime we start a new block, we're going to indent again from that. So I'm indenting, and I'm going to put my input is D, comma, CLK, semicolon. And then my output, and I'm going to do this. I know this already because I read it. It said use a non-blocking assignment, and I'm going to put this in an always block. So when I assign it in an always block, it needs to be labeled reg. So I'm going to put output reg and Q, semicolon. Okay, so at this point, yep, there we go. So all my errors went away. Everything is defined. I'm not doing anything yet, but I'm ready to go. Okay, so now let's take a look at our instructions. Use the code on page 4 of the lecture slides and use a non-blocking assignment. So if we go to the lecture slides, on page 4, we have this code here for module D flip-flop. And the only thing we don't have so far is always at positive edge clock Q equals D. So that's all we have to put in is our always block. So that's what we're going to put in. The difference is this, the Q equals D, is not non-blocking. So non-blocking is, so Q equals D is blocking. Blocking means that the Verilog compiler evaluates all the statements in order. So it does the first one and then the next one and the next one. So if you've changed something up above, then that new value will be used later on in the always block. With a non-blocking assignment, as soon as you enter the always block, the values of the variables are frozen. They're not all variables are frozen, but the variables that you're going to use when you use a non-blocking assignment, it's going to use the value of that variable when you entered the always block. So in this one where we have Q becomes D, it's going to be whatever D was when you entered the always block. So if you've changed D since then, it's not going to affect what Q is going to be. It's going to be what D was when you entered the always block. So we are supposed to use that non-blocking assignment. So now we'll go back. Well, let's just go back to slide 4. Remind ourselves, always at positive edge clock, Q equals D. So that's what we're going to add. So we got an always block. So always at open parentheses, positive edge, so positive edge space, our clock is CLK, close parentheses, and now enter. Now here I'm going to indent. I'm going to indent because I'm inside an always block. So everything that's in here is going to be indented. Now I just have one line. Since I just have one line, I don't need a begin and end. And my one line is going to be Q becomes D, and that's it. Okay, so and now I'm done. So I've done my entire code here. I don't have any errors, so I don't see any little red lines over here, no red squiggles, so that's good. So I'll save it. Okay, so now I need to do my constraints file. Now, if you go to the Moodle page and you look at Basys3 constraints file template, this is really handy so that you don't have to type all this and make typos like I would. So so we have here the set property for the different switches and what the names of the switches are and the LEDs and the segment display and everything is all right here. It's also in, you can find these things also in the Basys manual. I'm pretty sure you can. The Basys manual is also available. Somewhere. There it is, Basys3 manual. But we can just get them here. Now, if you, well, but actually, let me pull up here. Okay, so if you look at this file, this is the one that I was showing you that just kind of gives you the directions, the step-by-step on how to set up, how to program the Basys board. He has also included a nice picture. So if you're not in the lab and you want to see what the names of the switches are, you can zoom in and you can see this switch is R2, T1, U1, W2, R3, and so forth, going across that way. The LEDs, L1, P1, N3. So you've got those names right there. And then, well, I don't think it, yeah. So, so that's where you can see where those are. Okay, so going back here to my constraints file, no, going back here. So I want to use, well, let's see if we are given instructions. It says, in creating the constraint file, you can map input D to any switch and output Q to any LED. You should map the clock input to one of the push button switches of the Basys board labeled U18, T18, W19, T17, U17. These switches are near the center right of the board. So we'll come back and do the clock in a minute, but so we can use any switch. And so we have the switch all the way on the left is R2. So I'll use that one. That one is right here. So I'll copy that. I need to uncomment it, so I'll take the comment out. And this is for D. So I'm using this switch for D. So I'm replacing what's in these brackets with D. And for the LED, I'll use the first LED, which is L1. That's L1, and it is representing output Q. So I map it to Q. And now I have to say what the clock is. And so if we look here, we have the directions for the clock using pin U17. So I don't know if this copy and paste will work. I'll try it. Let's see. It didn't work very well, but I'll use it anyway, so I don't have to retype everything. Okay, so I'm going to put a little space in here, and this is just for me, my own personal information. These are my inputs. These are my outputs. This will be my clock. Okay, so remember I called my clock lowercase CLK, so I need to do that. So set property, package pin. Now this is indented a little bit. Get ports clock should be CLK. And then set property, okay, all that. Now the thing I need to change here is I need to change this to CLK IBUF. Okay, so I think I have everything now. Let me save that. That's saved. Okay, let's open the elaborated design. So you can do that even if you don't have the Basys board, and it'll show you a schematic. And so this takes a little while sometimes. It can. And whenever you're using this manual clock, you will get this warning. And this warning is saying that it doesn't like something, but it'll still run, and that's okay. So let's just say, okay. Okay, so now I'm going to look at my schematic and say, ask myself, does this look like what I expect it to look like? And the answer is yes, it does. Look, I've got a clock going into the clock input. I've got an input D going into D. I've got a flip-flop here. And look, it's even a D flip-flop. That's what I want. And my output is Q. So everything looks real good. Okay, so the next thing you can only do if you actually have a Basys board. And that will be to generate the bit stream. So I'll click on generate bit stream. Yes, and okay. And I can tell it's working because I can see up here on the top right where it's running the synthesized design. Okay, so now it finished generating the bit stream. I don't have any errors down here. If I had any errors, I would look at them and see what was going on and go back and look at my code and see if I could figure it out. Maybe in another video, we'll do some debugging. open the hardware manager and say, okay. And eventually I'll probably take this survey, but not right now. Okay, and then I'm going to go up here where it says no hardware target is open, open target, and then open new target. And local server. And I need to change this clock frequency down to the one at the very bottom. To that's a lot of hertz. However many hertz it is that's 30 gigahertz. Is that what that is? It's a lot of them. Anyway, it's the bottom one. And then next, and then finish. Now I do have the board plugged into my computer. And now I'm going to do program device up here. So program device. And it should have the correct bitstream file there. So program. Okay, so it's now programmed. So I stopped the share and I have this not mirrored, which actually means to me it's going to seem like it's in reverse. So I'll hold it like this. Okay, so I know it's programmed. I've got the green light up here, right there. Okay, and we programmed it for this switch and this LED. So it should be that if I turn that, and it didn't work. There we go, now it's working. So I turned the board off and then back on. Let's see, so yeah, it says target shut down. I am, just for fun, I'm going to refresh the device, make sure it actually is working. Refresh device, that device. Because could have been programmed with something I had on it before. Program device, program. Okay. Let's see what's going on. Okay, so I'll tell you, I forgot a very important part of what's going on. So I'm glad I made a mistake. So I can show you. So I reprogrammed the device. So I didn't change anything on the code, but I forgot the whole point of what we're doing is flip-flops. It changes on the positive clock edge, and we defined a clock. So what should happen? Let me stop the share. We defined the clock to be this bottom button on this little button array right here. The bottom button is the clock, and so when we press that, that advances the clock. So right now, my switch is off, and so D is 0, and so if I press the clock, I should not get the LED to light because it's 0. And in fact, nothing happens. So now if I flip the switch, so now D is 1. So now at the next clock edge, Q should become 1 and the light should come on. So if I press the button, or the clock, the light comes on, and it does. Now, if I advance the clock again, it should stay on because it's still at 1. Now, when I close the switch, it stays on because it's not at the clock edge. The clock edge happens when I press the button. So now I press the button and it goes off. Press the button again, stays off. Turn the switch, it's off, and it won't come back on until I press the button, and it's on. Okay, so that was doing the D flip-flop, and I'm going to stop it here.